talks, Brent. It's now the turn of Domenico Coiro, who's a full professor at the Department of Industrial Engineering Aerospace Division at the University of Naples, Federico II, in Italy. And I will just a moment, I will share the presentation.
By the way, thanks for inviting me here. It has been very interesting up to now. And with this presentation, I'm just going to show you what has been the last almost 40 years of my life working with small wind turbine as well as other topics. Okay. So I belong to the University of Naples, but at the same time, I'm also president of the Sea Power Consortium, which is a public-private consortium, non-profit, which university participated. And oh, okay, go ahead. And we are about 22 people working there, employed in this research consortium. And we have been working during the last 40 years on the 35 years on small, medium turbine, and that's the topic of today, but specifically also with marine currents turbine as well as wave energy converters. Plus, cash flow is mainly coming from, since the other two are more, let's say, up and down, are coming from project development of very large PV fields, about 100 megawatt each in Italy, specifically in the south of Italy. Go next. Take studies, I put some video. Okay, they're slow, but just to show you some project we have done. Down here, you see the first turbine for tidal currents vertical axis, 1998, set in Messina Strait. This is the first turbine in the world of this type. Then we are developing also a device for wave energy converter. You see a prototype of it, as well as vertical axis turbine for river power, which is a vertical axis without any holding struts, as you can see here.
You can keep the last sentence because there was the audio of the video.
Ah, so sorry, you can, yeah, you can. I tried to put off before, but probably didn't work. Okay, so here on the right, you have a river turbines mainly devoted for river. It's variable active pitch, and there's no holding arms like this, while this is a passive variable pitch, and it's self-starting. This is for tidal currents set in 1998. As I said, up here is a prototype of a system for wave generation. Go next. The more advanced system we have for water is for tidal currents. This is a sort of a kite. It stays steady. It's a single point moored, and when the current comes, the turbines rotates, and the whole system will rotate when you have a change when the current direction change. This is the first prototype set in the Venice Lagoon, slow current, 1.6 meters per second maximum. And now we have the second generation one, and hopefully 300 kilowatt is going to be set in Messina Strait in a couple of years. Go next. This is just some other topics. Okay, we use also our two facilities in my department. One is wind tunnel. I manage the wind tunnel. This can go up to 45 meters per second. We have been testing a lot of airfoils in the past, as well as wings and planes, obviously, but also for wind turbines. Then we have a largest naval tank at university level in Europe. It's 120 meters, 9 meters wide, and 4 meters deep. Very well suited for both tidal currents measurement and also for wave. And as you can see now, I will talk about this. And recently, we're heavily working with European project, two European projects in offshore, obviously offshore floating wind turbine, which is the hot topic now since the small wind practically has been cut out in Italy. Go next. distant past. We started back in 1991. I was designing an airfoil along with Jim Tangler and NRL for this wind turbine, for boats wind turbine. Then we tried vertical axis in the tunnel. We have done, this is my car back in 2005 to test the shrouded turbines. And this was equipped to measure the torque, power, and everything. And we also tested the relatively large wind, vertical axis wind turbine in 2009. And this is another type of a turbine tested in a large section of the tunnel. Okay, go ahead. These are all types of horizontal axis turbine we've been designing, built, and testing. 5 kilowatt passive pitch with balancing mass. It's a 6-meter diameter, so 5 kilowatts at about 9 meters per second. Then we've been designing, these have not been produced commercially, but we tested the Furling turbine 2.5, 1 kilowatt turbine, again tested on the field but not produced. And then we have supported this company here to produce the 60 kilowatt active pitch, as well as this one. We have become part of this company, 60 kilowatt with active pitch. And the latest, and they talk about a little bit more about this, it's a downwind passive turbine fixed pitch, 60 kilowatt with 28-meter diameter, and it gives 60 kilowatt at about 9 meters per second, specially suited for low wind speed cycles. All turbines have been designed according to EHA 61-1. So we have done all elastic and dynamic computation. Go next. Okay, this is just so you know. I mean, I didn't know how when you prepared on this field. People think that the small wind turbines are simpler than larger wind turbines. It is not the case, to my opinion at least. Large turbines are more complex, more costly, but these are more difficult to design because they work in a very bad condition regarding the wind turbines area. They have a low Reynolds number on airfoil, high centrifugal and gyroscopic forces when they move. So to put on a pitch control system is not an easy task because you have to follow the movement of a turbine, and fatigue lifetime is another important topic. Since the small wind turbine, they have 600 million of cycles, almost 1 billion. And for example, respect to airplane or large wind turbine, they have 100 million cycles. So fatigue often is a key point for designing the turbine. Go next. This example how it's important to design according to taking in account structural components. You can see the difference here. Steady wind, unsteady wind. This is a flapping moment, so very high difference between considering steady wind and unsteady wind. And this is rigid and flexible, both blades and tower. So if you have unsteady wind, but you keep everything rigid, so you stiff, you have this type of loads. While if you move it, I mean, if you take them, consider them flexible, then you have the difference is very high. So it's very important also in this class turbine, taking in account everything. By the way, if you use -2, it's easy, it's simpler, easier, but then you have oversides because they have some strict regulations. So in order to cope, go next one, to cope with the most important parameter, which is the cost of a turbine. We have next. Did you push it? Okay. The most important parameter is the cost, obviously. To keep the cost down, you have to know, you have to, let's say, predict very carefully the load, and you have to design and also the structural part such that to stay at the minimum in order to have, to stay in with levelize the cost of energy. This is an example of the turbine of 60 kilowatt. So the capital cost of the turbine ready to go is about 227,000 euro. And in a site with an average wind speed of 5.5, The energy produced with this turbine is 160,000 kilowatt hour, so 2,600 equivalent hours. And still, in this case, you end up with a levelized cost of energy of 18 euro cents per kilowatt hour, which is high. And without any, let's say, feed-in tariff supporting, it's difficult to stay, specifically when the wind speed is not very high. Go next. And this is the case of Italian sites, most of them. So you need tools, obviously, more accurate tools, like CFD in this case, lamination plan, accurate designing of a structural part in order to save construction, manufacturing time, and also bill of material, reducing bill of material, so accurate lamination, and obviously finite element model to arrive to an optimized blade. The next, optimization means optimize at the same time both aerodynamics and structural, not separately, which is a key point to have a good blade. This is an example of testing at the company site. In this case, we were testing both the generator and actuator pitch. This is for 60 kilowatt active pitch control. This is a bench test, dry bench test for 5 kilowatt permanent magnet generator for performance of the generator. In this case, at that time, we designed and built the generator. This is the large test with the generator here, permanent magnet direct drive generator, and at the same time using let's say, the pitch actuator to see its performance. This is a torque meter to measure power and torque. Go next. Same time, you need accurate modeling of modal characterization of the blades. So you see here an example of the small blades in the wind tunnel, fully equipped to measure the shape of modes. And here you see measurements of the modal response for a full-scale blade on the field. So here you see how to characterize the Campbell diagram, as Brand was saying just 10 minutes ago, the diagram to see in reality what is the response of the blade under gas, natural response of the blades. Go next. And at the same time, you need to perform, this is a braking test of blades in the company, and this is the fatigue test on the similar blade. Actually, I left that because you can hear the noise. So when the blade breaks, but then they cannot. Okay. Oops. Can you try now? So this is, we break the blade here to see how was the breaking point. And in this case here, we performed the fatigue test and applying at the same time, I think this is one rare test as far as I know, applying the centrifugal force. So we were testing the blade in fatigue, and at the same time, we were applying, I think, 10 tons of centrifugal force on the blade to see if there were an effect on the centrifugal force. So this video showed the test in the company. Okay, go next. This is an example of how we set sometimes, strain gauges on the tower base to measure deformation, and then after calibrating to see what is the base moments induced by the turbine. And this system here has been used for the rotating case. We put strain gauges on the blades to see the loads on the blades during the while the rotor is turning. Go next. Okay, this is the turbine I will talk a little bit more about. It's 28-meter diameter. As you know, here 28-meter diameter corresponds roughly to 300 or 250 kilowatt. In this case, it's 60 kilowatt. So it's been designed for sites with for 4.5 meters average wind speed. So wind speed is downwind, passive, fixed pitch, so stall control. And for example, here is the study of main accessibility in the nacelle. So everything has been designed, has been really pushed to the limit to keep the low cost of all components as well as the manufacturing time. So everything has been done in order to reduce the manwork, which is one of the higher part of the cost when you build the turbine. Go ahead. This is the difference in kilowatt hour respect the standard 60 kilowatt turbine. This turbine, obviously, rough condition, I mean, assuming rough condition on the blades is, at same average speed, he has almost 60% annual energy more respect to the standard turbine, obviously, since the diameter is larger. Go next. Advantages, obviously, robustness respect to pitch regulated turbine, less maintenance, probably lower manufacturing maintenance cost. Obviously, stall-induced vibrations, the rotational effect, I will show you a little bit more. And you really need to design the airfoils first and then the 3D blade very accurately in order to have, let's say, to have the turbine and the blade perform as you think. So you need the multi-objective optimization. Go ahead. Next one. This is an example of rotational or centrifugal pumping, as we call. If you do not take in account this area here, which is near the root, properly taking into account, and then you mix both element-based, boundary element-based method with CFD, you are not able to predict the performance of the turbine. So you have to combine. You have to run some cases with CFD codes, and then you have to combine the results to modify the airfoil performance in order to be able to capture the let's say attachment, the vortex, which stays here when the flow is attached. So if you use only the BEM methods, you get separated flow, while in reality it is attached flow. So you have to pay attention in this area when you design these turbines. Go ahead. Beside the low Reynolds number, here you can see when the blade is here. This is the answer, the response, shaft bending moment. When the blade stay here, which is in post-stall conditions, obviously the response is much higher. So you have to take in account this stall response. Otherwise, is not the loads are not correctly predicted. Go next. Oh, this is an assembly. So we reduced the assembling time of this turbine 50% more. This first prototype, actually, we put the brake on the low-speed shaft. So we said, okay, this is for security, for safety reason. We have two independent systems to brake the turbine, but let's put this on the slow speed shaft. And then we're supposed to change and to modify and to put it on high speed shaft. But then the company closed after, I think we installed something like 12 or 15 of these turbines. They were rushing and they did not change at that time the generator. So the turbines now running, are still running. There are many of them are with a large brake here on the low speed shaft. Go next. These are the performance of the turbine measured. These are not the final one, actually. It's a little hold, this picture, compared with the numerical prediction. Go next. This is the turbine again. This is the interface that the user can go and check all components, all temperature, performance, whatever. And this is the turbine installed. Go next. 36 meters, the height of it. Just a recap of all turbines have been designed. H5. Now we have the manufacturer drawing available. Nobody is producing this turbine. This is with the spring passive stall. The only thing about this, I'm happy because it was abandoned on the testing site for maybe 5-6 years, and has been running alone without any problem, even if nobody was putting it down. Okay, go next. these are the performance measured with taking 1 second sample at the time. So it was abandoned this site. So as you can see, the performance is quite well, 5 meters per second. I mean, 5 kilowatt at about 9 meters per second, as predicted. This is the prediction. Go next. This is our CK6 again. The company closed. Now we have all manufactured drawing available. Permanent magnet, active pitch, diameter. We changed the blade a couple of times. So the beginning was 18 meters. Then we rebladed at 22 meters. The generator has been designed by us. So it's very robust generator. And this year at 5.5, has been, there are about 80 turbines of this. At 5.5, it produces roughly, well, at least little less of this, but roughly 140,000 kilowatt hour. Go next. And this is the last one we have done. This is the cheapest, I would say, for a company, which is up to 225. Has not been fully tested yet, I think, but this is the lowest cost for this turbine. Is about 100,000 euro, fully ready to go. It's fixed pitch, upwind, active yaw, and it goes. It's called the 125. But the objective is to have 125,000 kilowatt hour at 5.5 meters per second. And even if it's not been completely tested, to my opinion, they have sold, I don't know, maybe 30 or 40 turbines already. They're running around. Go next. All these turbines are located here. So we have had the chance to keep maintenance. So we have followed all the maintenance procedure for all these 3 turbines, Optiturb, CK600, and Simply 60, the large one. Go next. And as you can see, I just recorded all the failure that we have had in these last 15 years, 15, 20 years. And as you can see, the majority of failures goes to electrical system. And in the electrical system, I mean electrical panel. Then we have, enough failure on control unit is PLC, often stops and doesn't work. 3% on sensors like cups and stuff. Why this? Because probably the companies, they have not bought the top of the class. And so sometimes the sensors, they break, so you have to change. Some problems with the hydraulic system. But anyway, in our case, these are the percentage of failures. Go next. And these are the same represented in a different way, maybe more clear than that. So you can see the number, the percentage of the failure regarding the different components. Go next. Okay, finish this last one. This is just to show you how important is the policy in the country. This is supposed from 2004. This is an idle, let's say, growth in installing renewable energy. So you would think that, in a country, you go like this. So you continuous in steady, you increase the turbine number, installed turbine numbers. Go next. While the real situation has been like this in our country. So we have had the very high, installation gigawatt installed between 2008 and 2014, and then again down. And now recently we're still growing like that, but here there are not small turbines, only large turbines. And now to cope with the European, let's say, agreement to reach 50% of renewables for the 2030, then we have to grow with this rate, only with offshore, I think, floating wind turbine, at least in Italy, in order to reach the goal that Italy has, which is up here for the gigawatt needed in order to comply with the agreement. And so this is show that politicians and the policy is very important when you want to keep a sector increasing and steadily increasing in terms of turbines installed. Okay, thank you. Then the next, I think, is finished. This is where I come from. It's Pozzuoli near Beni. Okay. Thanks.
Thank you, Domenico. I can see there are some questions in the chat. Let me, we need to stop sharing, but so here you have the questions.
No. The current turbine, here, right? The current turbine is standing still in the water. It's not oscillating back and forth or rotating like Minesto turbine. There is another turbine which is been tested. It's the Minesto, but it's much smaller, by the way. And in this case, it just stays still in the water. Actually, it stays vertical when there is no current. When the current comes, it goes back and down, or a little down, because obviously the drag will push it down, and then stand still. And the single point moored. No, from one side to other side, when the current changes, that the current goes to zero, slack water, then the turbine stands still. And then when the current changes, thanks to the tail, the turbine will follow the direction of the current and will again align, self-align to the new direction of the current. Is it a belt drive? No, nothing belt drive. All planetary gear assembly. No. Any other question?
No, doesn't look like. Thank you very much.
Okay, thank you.